We're now going to dive deeper into this, and we're going to try to understand exactly what's going on over here. We're going to start off with something called compressional warming. We're going to start speaking about the heat dome. There's a number of sources, there's a number of places where you can get a definition for a heat dome. I happen to be reading from AccuWeather. What AccuWeather says, a dome of heat is essentially an area of high pressure that extends to most levels of the atmosphere, from near the ground to the level where jets fly, says AccuWeather senior meteorologist Alex Sosnowski. Since air generally sinks beneath a high-pressure area, it warms up because the air is being compressed as it descends. We're going to talk about that in just a second. However, when the air aloft is already warm to begin with, it gets even warmer as it sinks closer to the ground. As the heat dome sticks around, this feedback loop continues to produce warmer weather at the surface layer of the atmosphere. Okay, that's what AccuWeather says. However, this needs further explanation because we brought in a concept called compressional warming. So I wanted to explain that for a moment. I think it's important to understand it if you want to understand what's going on. So for this, I turned to a website. It's called kxan.com. But really, all of this is available on the National Weather Service website. As a high-pressure system, and now it could be, we should explain high pressure, but maybe we'll do that. But as a high-pressure system sits over an area and has air compressing downwards, this also warms as it does so. Okay, now here's why. So high pressure is where the air is sinking. The air is sinking. In the northern hemisphere, it's sinking in a clockwise manner. Therefore, if you have a Bermuda high pressure, the winds are around the Bermuda high, they're going clockwise. And this air mass could extend about 1,000 miles in every direction. So it could go into the Gulf of Mexico, and it would bring even a southwest wind to St. Louis, Missouri, despite the fact that the high pressure is 1,000 miles southeast of St. Louis. And if the high pressure is blowing winds out, you would think it would be blowing a southeast wind to a city like St. Louis. But because of the clockwise thing, you could actually end up with a southwest wind. But the high pressure, the air is blowing downwards. And as the air blows downwards and there is pressure, even though it looks to us like the air is invisible and it feels like the air has no pressure, air does have pressure. Why does compressing air warm? So it says here, this is because in meteorology, the ideal gas law states that as a gas, in our case, all the gases in the atmosphere, so the whole atmosphere, it decreases pressure and temperatures also decrease. So it says as a gas decreases pressure, temperatures also decrease. That's the law. There's a rule like that. And as gas increases pressure, temperatures also increase. So if you should have rapidly sinking air, then you're going to see a rapid increase in those temperatures. In the case of, in whatever case this article is speaking about, there was a cold front which was headed into that area as a high pressure was slowly moving away. The cold air associated with it is more dense than the warm, condensed air of the high pressure and stays close to the surface. As the high moves away, winds at the surface will be coming out of the southwest. This is a different situation, which is another form of compressional heating. This takes place because winds will be coming from a higher and drier environment. And as this air moves from the higher elevations of West Texas, again, this is not the heat wave we're speaking about now. This is an article from a previous weather event. As this air moves from the higher elevations of West Texas to the lower elevations of Central Texas, the ideal gas law kicks into gear. This increasing the temperature as the pressure increases. Additionally, as our cold front marches towards the high pressure, the warm air is forced up and over the cold front. But as it does so, it also compresses and squeezes the warm air between the cold front and the center of high pressure, causing it to warm. So in all, it's going to get downright hot. Again, this is in regards to a different weather event. I'll read you a different definition. This comes from Fox 24, KNWA, written by Alexander Williams. Weather 101, compressional warming. And it says like this: I'm sure you have heard our chief meteorologist Dan Scoff mention the term compressional warming whenever a powerful cold front is headed our way. It is the reason why the temperatures often heat up quite a bit the day before the front rolls into town. In this edition of Weather Word of the Week, we're going to explore this important topic. What is it? Compressional warming is exactly what it sounds like, warming the air by compressing or squeezing it. The molecules of the air mass get pressed together, increasing the friction, which in return increases the temperature. Imagine a bike pump. Have you ever noticed that after pumping your bike tires up, that the hose of the pump gets pretty warm? This is because as you push the pump down, you are pressing the air molecules against each other. As mentioned above, this increases the friction of the air molecules, which in turn produces heat as a byproduct. Physically, this is a direct application of Newton's first law of thermodynamics. So let's apply this same concept to the atmosphere. Okay, now we're going to speak about compressional warming along a cold front. That's not the case we have today in Texas, but as discussed in a previous episode of Weather 101, a cold front has a sloped surface along its leading edge. The steepness of a cold front slope depends on the strength of the cold air mass behind it. The steeper the slope, the greater the amount of compressional warming ahead of it. This means that the stronger the cold front moving into town, the greater the temperature will rise ahead of it. Another factor affecting the amount of compressional warming is the timing of the frontal passage. If the front pushed through overnight into the morning, the warming will be significantly less compared to an afternoon frontal passage. The afternoon allows the daily solar heating to combine with the compressional warming, thereby increasing the air temperature quite a bit more. It gives an example of compressional warming. Notice how warm the temperatures were before the cold front pushed through. In this particular case, they were in the upper 70s to mid-70s across the area. This was back in February over some town. And we're speaking about northwest Arkansas, actually. The National Weather Service over here tells us what a heat dome is. Heat dome occurs when the atmosphere traps hot ocean air like a lid or a cap. A team of scientists funded by the NOAA MAP program investigated what triggers heat domes and found the main cause was a strong change or gradient in ocean temperatures from west to east in the tropical Pacific Ocean during the preceding winter. The Royal Meteorological Society tells us, what is a heat dome? A heat dome is created when an area of high pressure stays over the same area for days or even weeks, trapping very warm air underneath, rather like a lid on a pot. At other latitudes, pressure systems usually move from west to east, but sometimes they can get blocked, often when the jet stream weakens and buckles. The jet stream is a core of strong winds high above the Earth's surface that helps to prevent and steer areas of low pressure around. The position and strength of the jet stream can lead to blocking situations, such as an omega block, where high pressure ends up sandwiched between two low pressure systems, forming a shape like the Greek letter omega. The problem with a stubborn area of high pressure is that already warm or hot air trapped under the high will become hotter and hotter, creating a heat dome. Hot air will rise into the atmosphere, but high pressure acts as a lid and causes the air to subside or sink. As the air sinks, it warms by compression and the heat builds. The ground also warms, losing moisture and making it easier to heat even more. Until the pressure pattern changes, the high will continue to exacerbate the high conditions, bringing a risk of wildfires, drought, and heat health issues.